This is question number 4 from the 2022 AP Calc A, B, and BC free response set. And this is a question involving a table of values. It's kind of a weird table of values. It's involving derivative values rather than function values, so that's something you've got to be kind of cautious with on your way through this. But the context here is that we've got an ice sculpture that melts in a way that can be modeled by a cone that maintains its conical shape as it decreases in size. The radius of the base of the cone is given by a twice differentiable function r. R of t is measured in centimeters, t is measured in days. The table above gives values of r prime of t, the rate of change of the radius, or the derivative of the radius, over the time interval 0 to 12. So in part A, we're asked to approximate r double prime of 8.5. They tell us to use the average rate of change. Usually they would just say approximate r double prime of 8.5. They typically ask for units of measure and an interpretation. They kind of left those things out here. But for r double prime of 8.5, we'd hopefully recognize 8.5 is smack dab in the middle of that interval. So if we use a slope calculation, a standard slope calculation, with the ordered pair 7, negative 4.4 and 10, negative 3.8, what we're going to end up with after doing that slope calculation is 0.2 centimeters per day per day. Now this expression right here, this fraction with the differences being shown, that would receive full credit. You don't have to waste time, take on risk to try to simplify it to 0.2 here. The units should be pretty obvious. Your y values in the, I shouldn't call them y values, your values in the top of the slope calculation are measured in centimeters per day, and then your values in the denominator are measured in days. So we're looking at centimeters per day or centimeters per day squared. If you were asked to give the interpretation, this would mean that the rate of change of the radius is increasing by 0.2 centimeters per day at 8.5 days. Part B asks us to try to decide if there's a time for which r prime of t is equal to negative 6. Anytime you're asked to justify whether or not there's got to be a function value, a derivative value, it's almost always a situation where you're going to either go with the mean value theorem or the intermediate value theorem. So at the beginning of this video, I said you've got to be cautious of the fact that you really have derivative values in the table here. Normally what I tell my students is if you're trying to ensure the value of a derivative, you're going to typically be going mean value theorem, right? The conclusion of the mean value theorem guarantees the value of a certain number for a derivative. So in this case, though, we've got to be able to recognize that we actually have access to derivative values. So if the derivative value goes from negative 6.1 to negative 5 as t spans from 0 to 3, there's no way that we can get from this derivative value to this derivative value without crossing the derivative value of negative 6 somewhere in between. Now, that's my thinking, but my justification, my arguments that I have to get onto the page would be if I'm using the argument that I just made, the function that I'm applying those arguments to has to be continuous. So how do I know that r prime of t is continuous? Because I could jump from negative 6.1 clear up to negative 5 without crossing any values in between if my graph has like a jump discontinuity in it or something goofy happening in between 0 and 3. Well, they tell us that r is twice differentiable. If r is twice differentiable, that means the first derivative always exists, and therefore the first derivative is continuous. So since r is twice differentiable, r prime of t is continuous. Since we've got a derivative value of negative 6.1 at 0 and negative 5 at 3, and negative 6 falls between those two values, or negative 6 is intermediate to those two values, the intermediate value theorem is going to ensure that r prime of t is going to equal that intermediate value, as well as all other intermediate values, at least once on the interval from 0 to 3. Part C asks to use a right Riemann sum with 4 subintervals indicated by the table to approximate the value of this definite integral. Again, I'm kind of surprised that they didn't ask us to do any interpretation of this or list units, so that was kind of left out. We'll talk about that after we show the calculation that needs to happen here. So if you're doing a right Riemann sum, The first interval indicated by the table spans the t-axis from 0 to 3. So the width of that interval is 3 units. Now the right endpoint of this interval is obviously 3. I'm going to use the y value from that right endpoint, -5, to represent the height of my first rectangle. So my first rectangle's area is going to be 3 times -5. My next rectangle spans the t-axis from 3 to 7. So the width of that rectangle is 4, right endpoint is 7. I use the y value at 7 for the height of that. Next width is 3, right endpoint y value is -3.8, and then my last interval has a width of 2, and my right endpoint y value is -3.5. Give me 1 second. I usually put the simplified calculation. This is what I have would receive full credit on the AP exam. You don't have to simplify. You don't have to carry out arithmetic like this in your FRQs, but I will try to find out the value of this in case you went clear to the end. Again, you take on risk, you waste time if you do that, but I'll go ahead and get that on the screen real fast. So that value should end up being -51. If you were asked to interpret units, if you think about what we have right here for the units of r prime of t, centimeters per day, units of dt have the same units as t has, so this would be centimeters per day times days. The units of this would be centimeters. So the interpretation of this would be that the radius of the cone has shrunk by approximately 51 centimeters from day 0 to day 12. Again, not part of this problem, but that's usually what you're going to find in a question that asks similar sorts of things. Last part of this, I think, is the toughest part of it. So they say the height of the cone decreases at a rate of 2 centimeters per day. Now I read that sentence and I right away I think related rates, right? They give me the rate of change of the height of the cone. Moving forward, it says at time 3 days, the radius is 100 centimeters, the height is 50 centimeters. Find the rate of change of the volume of the cone with respect to time in cubic centimeters per day at time t equals 3 days. So we are asked to find the rate of change of volume. So they give us dH dt. We have access to dr dt across this bottom row of the table, and they're asking us to find dV dt. So I like to identify what my rates are. I kind of did that verbally just a few seconds ago. dH dt at time 3, now it is negative, right? So one thing you have to be cautious about with related rate situations, if they tell you verbally that something's decreasing, the rate of change of that quantity has to manually be made negative. Now dr dt, r is also changing over time, but that's something at time 3 that we have access to from the table. So at time 3, dr dt is -5. And what we want to know is we want to know the value of dV dt at that same time. Now to find the derivative of volume, you do have to be careful with this. You are going to have to use a product rule. The radius of the cone is changing as the cone melts. The height of the cone is also changing as the cone melts. So R and H both change over time, and because I'm taking my derivative with respect to T, I'm going to have to use a product rule. So when I apply my product rule to, so I thought of this as the first part of my product, right? So 1/3 pi r squared. When I take the derivative of that, I multiply the coefficient by the exponent 2, subtract 1 from the exponent, but then because r changes over time, I do have to finish off a little chain rule and multiply by the derivative of the inner function. So the beginning of my product rule, the derivative of the first part of the product is this, times the original second part of the product, plus the original first part of the product, times the derivative of the second part of the product. If you go ahead and substitute in, you don't have to solve for anything here because dV dt is already isolated, so dV dt evaluated at time 3 is just going to amount to us putting 100 in place of the r, -5 in place of the dr dt, 50 in place of the h. You see 100 in place of the r one more time, -2 in place of the dH dt. You would be wasting time and taking on risk if you tried to turn this line right here into what it simplifies to. You know, without a calculator, it takes a decent amount of time, lots of little places where you can make a mistake to try to get from what you have across the line here to this final answer line. But this back here receives full credit on the AP exam. So you have to kind of pay attention to what your professor, what your teacher is asking you to do with regard to simplification. If you're prepping for the AP exam, leave your answer like the line I highlighted.